In this video, I will be covering introductory material to chemical reaction kinetics. The primary source of information for this video is Discovering Design with Chemistry by Dr. J. Wiley. We already know how to determine if a reaction will proceed using Gibbs free energy. The next question a chemist must ask themselves is, how fast will the reaction proceed? Take, for example, the following reaction. A goes to B. The rate of the reaction can be defined as the rate and change in concentration of reactants over time. Because the reactant is being converted to product A, the concentration of A will decrease over time, making the rate of change negative. Because there is one-to-one stoichiometry between the reactants and products, the rate of decomposition of reactants will be equal to the rate of formation of the products. To see this concept in a more practical light, let's look at the formation of copper sulfide from copper and sulfur. Because the stoichiometric coefficients are equal, the rate of decomposition of the reactants and formation of products will be equal and opposite. Let's look at an example of the reaction shown on the previous slide. Assume the tabulated concentrations are recorded over a 10th second interval. As you can see, the concentrations of both the reactants, copper and sulfur, are decreasing over time while the concentration of the products, copper sulfide, is increasing. The rate of change in concentration is calculated by subtracting the initial concentration from the final concentration. This value is divided by the time change to determine the rate. As you can see, the reaction rate is equal across all species as expected. There are three primary factors that influence the kinetics of a reaction. First is the concentration of the reactants. The higher the concentration, the faster a reaction will generally progress. In equilibrium reactions, which will be covered in the next video, this concept is displayed using Le Chatelier's principle. The second primary factor influencing the kinetics of a reaction is the reaction surface area. The larger the shared surface area between the reactants per unit volume, the greater the reaction rate will be. The third factor is the reaction temperature. Depending on if the reaction is endothermic or exothermic, the reaction temperature can influence how fast the reaction will proceed. Before I further discuss how concentration, surface area, and temperature affect reaction kinetics, it's important to understand collision theory. Collision theory boils down to the concept that reactions progress when electrons are transferred from one molecule to another. In order for electrons to be transferred, two reactants must effectively collide, or at least be in very close proximity to each other for the formation of the product. If the reactants do not get close together, the reaction will not progress. Because the electrons revolve around the exterior of the nucleus of each atom, it can be very difficult to get effective collisions between molecules because of the repulsion from negative charges. With enough momentum in the right direction, however, it is possible for the repulsion to be overpowered and have effective collision occur. Just because two molecules collide, however, does not mean the reaction will progress. If the collision that occurs is between two atoms that can't transfer electrons, you'll learn a little bit more about this concept in organic chemistry. This is called an ineffective collision, and the products do not form. Take, for example, the reaction of carbon monoxide and nitrogen dioxide to form carbon dioxide and nitrogen monoxide. Should the carbons collide with the nitrogen, no electrons will be transferred, and no products will be formed. On the other hand, if the carbon of the carbon dioxide combines with an oxygen of the nitrogen dioxide, electrons will be transferred and the products will be formed. Let's take a deeper look into how the concentration of reactants affect the kinetics of a reaction. If you consider a room crowded with people, the probability that two people will crash into each other or bump into a wall is much higher than if there were only a few people in the room of the same size. The same is true for concentration. The higher the concentration of reactants, the higher the probability that an effective collision will occur, and the faster the reactants will be converted into products. The effect of reaction surface area on reaction rate is a bit more difficult to understand. For the case of this example, consider a group of people in a very large room compared to another group of people in a very small room. The probability that somebody bumps into a wall in the small room is much higher than the probability of the same event occurring in the larger room. The concept of surface area can be difficult to visualize for homogeneous liquid systems, so imagine the oxidation of solid carbon by oxygen gas. The oxygen gas only permeates the carbon at the exposed surface, so if you maximize the surface area, you also maximize the area where oxygen and copper have contact and react, which will increase the reaction rate. Changing the temperature of a reaction will also change the rate of a reaction. Increasing the temperature of a reaction increases the rate at which molecules move. Consider a room example from before. There are two rooms with the same number of people in them, but in one room people are running and in the other room people are walking. It's more likely a collision will occur in the room where people are running than in the room where people are walking. In the same way, it is more likely collisions will occur between reactants when they are moving at high speeds than when they are running at low speeds in most cases. Power laws are often used to describe kinetics for a given reaction. For forward reactions, the rate law can be written as the product of reactants concentrations raised to some power. Consider the shown reaction of A plus B goes to C plus D. A generic rate equation for the reaction is shown below. RA is the reaction rate and always has units of moles per liter second. K is the rate constant and is generally constant for a given temperature. Calculation of this constant is a bit too advanced for this video, but eventually you'll learn how to calculate it using the Arrhenius equation. We will solve for it algebraically in a later example. A and B in brackets are the concentrations of components A and B respectively. X and Y, the exponents of A and B, are called the order of the reactions with respect to each component. The overall order of the reaction is equal to X plus Y. To take a more practical approach than A plus B goes to C plus D, let's look at carbon monoxide plus nitrogen dioxide goes to carbon dioxide plus nitrogen monoxide. Pretend we have a set of reaction data that allows us to write the following equation. RA is equal to K times the concentration of nitrogen dioxide squared times the concentration of carbon monoxide. The reaction is second order with respect to nitrogen dioxide because of the exponent of nitrogen dioxide. It's 2. Is first order with respect to carbon monoxide because even though there is no exponent shown, just like in algebra we assume a 1. The overall reaction order is 3 because 2 plus 1 is equal to 3. Or suppose the rate equation is written as follows. RA is equal to the rate constant times the concentration of nitrogen dioxide. The reaction is first order with respect to nitrogen dioxide, 0 order with respect to carbon monoxide, and the overall order of the reaction is 1 plus 0 or 1. We know from earlier that the reaction rates have units of mole per liter seconds, or molarity per second, but I never mentioned the units for the rate constant. This is because the units for the rate constant K are dependent on the order of the reaction. Because concentration is always in units of mole per liter, the units of K can be found through a process called dimensional analysis. Let's take a look at the first example from the previous slide, for example, and set up the rate equation with the units in place of the variables. The units for K can be solved for just like an algebraic equation. Molarity per seconds is equal to K times molarity cubed. Solving for K's units, we find that K has units of 1 over seconds times molarity squared, or liters squared per seconds times moles squared. Dimensional analysis can be pretty confusing the first times you do it, so it's a good idea to double check your work. We will plug in the units for concentration, reaction rate, and the units we solved for the rate constant into the rate equation. As you can see, we have moles per liter seconds is equal to liters squared per seconds times moles squared times moles per liter cubed. We can cancel liters squared in both the numerator and the denominator on the right-hand side. Likewise, mole squared over mole squared cancels. Now that we cannot cancel anything else, we see that the units on the left-hand side match the units on the right-hand side of the equation. Therefore, our dimensional analysis shows that the rate constant units are verified. Even though the rate constant is constant for a given set of reaction conditions, the rate of the reaction is not. As the reaction progresses, the reactants are converted to products, meaning that the concentration of the reactants is decreasing over time. Because the reaction rate is dependent on the reactants' concentrations, this means that the rate of the reaction will generally decrease over the course of the reaction. The main exception to this rule is when the overall reaction order is zero, meaning the reaction rate is completely independent of reactant concentration. Another way to visualize this concept is to observe the reaction coordinate in terms of reactant and product concentrations. As the reaction progresses, the concentration of the reactants will continually decrease while the concentration of the products increases. At some point, the concentration of the reactants will get so low that the reaction effectively comes to a stop. In the next video, we will learn about some cases where the reactants and products reach a state of equilibrium. But for the purpose of learning kinetics, let's just assume that the reaction goes to completion as the concentrations of reactants approach zero. Up to this point, all the rate equations and their orders have been given. But how do chemists determine the reaction orders? I'm going to walk you through the process of determining the reaction order and algebraic calculation of the rate constant from experimental data. The best way to design an experiment for determining rate law is to allow a reaction to progress several times, each time holding the concentration of one reactant constant. The first step in the general strategy is to select two trials for each reactant where the other reactant concentration was held constant. In this example, we can determine that the order with respect to methane using trials 1 and 3, where oxygen concentration was held constant at 0.6 molar. Likewise, we can determine the order with respect to oxygen using trials 1 and 2, when the methane concentration was held constant at 0.2 molar. The next step in the general strategy is to write the rate equations for the trials that we determined in step 1. Because we do not know the orders with respect to each component, we will leave them as variables x and y, and we will leave the rate constant as a variable k as well. Step 3 of the strategy is to divide equation 1 by equation 2 for each component in part 2. This is a valid operation as laws of algebra apply. Step 4 is to cancel like terms. For both equations, k over k cancels. For the methane, we can cancel 0.6 molar to the y power because it is in both the numerator and the denominator. For oxygen, we can cancel 0.2 molar raised to the x power for the same reason. The fifth step of the strategy is where it gets fun. In this step, we reduce each equation and solve for x and y. Start by dividing the left-hand side of each equation. Because the numerator and the denominator of the right-hand side of each equation is raised to the same exponent, we can simplify by dividing 0.2 by 0.5 raising to the x power for methane, and 0.6 by 0.4 and raising to the power of y for oxygen. This gets us the equality 0.16 is equal to 0.4 to the x power, and 3.37 equals 1.5 raised to the y power. We can now solve for x and y by taking the natural log of both sides and dividing the left-hand side of the equation. By doing this, we see that x is equal to 2 and y is equal to 3. The next step is to place the values we calculated for x and y back into the rate equation. At this point, we know the order with respect to each reactant, so we can also find the overall order, which is the sum of x and y, or 5. The last step is to find the value of the rate constant by selecting a data set from one of the 3 trials and substituting the reaction rate and concentrations into the rate equation. Simplifying further, we find k is equal to 10 1/2 times molarity to the 4th power. The final rate equation can now be written and solved for in terms of values of the values we found for x, y, and k. The rate constant is an important part of the rate equation because it contains kinetic information on the temperature and activation energy of the reaction. Consider this plot of the rate constant versus temperature at varied activation energies. As the activation energy of a reactant decreases, the rate constant increases for a given temperature. Think back to what you know about reaction thermodynamics. The activation energy is the amount of energy required to be input to a system before the reaction can progress. If this energy requirement is lower, the reaction can progress faster. Additionally, the rate constant is directly proportional to the reaction rate. Therefore, it makes sense that as the activation energy decreases, the rate and rate constant for each reaction will increase. In summary, we can conclude that as the temperature of a reaction increases, the rate constant will also generally increase. Furthermore, as the activation energy of a reaction increases, the rate constant will decrease. That was a lot of information to take in. Think of it this way. Consider the reaction coordinate, where the reaction progresses along the green curve, and the required activation energy is represented by the blue arrow. Then consider another reaction that progresses along the red line, but has a lower activation energy represented by the yellow arrow. Because there is a lower energy barrier to progress the reaction with the lower activation energy, the reaction will go to completion more quickly than the reaction with the higher activation energy. So what if the reaction we have has a high activation energy, but we want to progress it more quickly? In cases like this, we will add a catalyst, which lowers the activation energy of a reaction without being consumed within the reaction. It is important to note that the same reaction will occur, and the enthalpy change of the reaction that is catalyzed is unchanged from the enthalpy of the reaction that is uncatalyzed. There are two categories of catalysts we will discuss. The first is homogeneous catalysts. Knowledge of the Greek roots of the word homogeneous can help us understanding how the catalyst interacts with the reactants. The root homo means same, while genus means kind, gender, race, or stock. Therefore, a homogeneous catalysts are catalysts that react in the same phase as the reactions they catalyze. Let's look at an example. Say we want to progress the reaction trioxygen goes to dioxygen. This reaction progresses extremely slow due to a high activation energy. To increase the rate of the reaction, nitrogen monoxide can be added as a catalyst. Another reaction that will simultaneously occur is the decomposition of trioxygen to dioxygen and monoxygen. While these two reactions progress, the products of each reaction will further react, converting nitrogen dioxide and oxygen to nitrogen monoxide and dioxygen. Notice that the last step of this series of reactions, the catalyst is consumed in the first step and is regenerated in the final step. Additionally, the intermediate products, nitrogen dioxide and oxygen, are produced in the first and second reactions but consumed in the third reaction. In conclusion, if we sum all three reactions, we see that after canceling terms that appear on both sides, the reaction is reduced to 2 trioxygens go to 3 dioxygens. Therefore, the same net reaction occurs, but it will progress much more quickly due to lower activation energy of each reaction step. Also note that all this occurs in the gas phase, making it a homogeneous catalytic reaction. The second type of catalyst we will cover is heterogeneous catalysts. The Greek root hetero means different, so a heterogeneous catalyst is a catalyst that does not react in the same phase as the reaction it catalyzes. So how is this different from a homogeneous catalyst? Well, consider two molecules. They may be in the same phase or in different phases from each other, but they have a level of repulsion from each other, most likely from electron activity. However, they're both attracted to this solid state catalyst, or it could be any other state catalyst, but solid is probably the most common. So they're both attracted to this catalyst, and so they will both bind to the surface. When they bind to the surface, they are in closer in proximity to each other than if they were unbound to the surface based on their repulsion. When they're bound to this surface and they're closer to each other, they're able to transfer electrons to one another, allowing them to react and form the product. The product is then free to leave from the surface of the catalyst, leaving the catalyst unchanged. Thanks for watching, and I hope you enjoyed learning more about kinetics.